Okay, hi. My name is Dave Wong. I'm a director of memory product planning for Samsung Semiconductor, based out of San Jose. Today, I'm going to talk to you a little bit about two slightly different topics, actually PIM and CXL memory, but they're tied together. And time is limited, so let's get started. There's a lot to talk about. So we'll just start it with a huge disclaimer. All this wordy stuff just means is that I will try to, provide to you the most accurate information I know, but business situations change, and I may misspeak inadvertently. So don't hold anything against me or Samsung. And so I'll try to do the best I can, and let's go. Okay. So that's my agenda today. I'm going to talk about processing and memory, and then AXDIMM, which is actually what I refer to as processing near memory. And then I'll talk a bit about CXL memory, and then our software effort in doing memory tiering, as you heard a lot about today, about the efforts for the need for software support for memory tiering. And this is our effort for Scalable Memory Development Kit. There will be a demo at OCP by the Samsung engineers. They actually flew in from Korea for this. And then I'll finish with some concluding remarks. So let's start with PIM, processing memory. What is processing memory, right? So processing memory is not a new idea. It's an old idea. It's been around for decades. People want to put some processing capability within the memory device itself to sort of alleviate the bandwidth constraint between the compute element and the memory element. But it's sort of goes away, comes back, and so now it's kind of back again. And the reason why it's kind of be backing it, because we're actually running out of ways to alleviate the bandwidth constraint between the processing element and the memory element. The way that we've been sort of trying to get around this bandwidth constraint historically is just try to make wider buses faster and just get more bandwidth, right? And we're at a stage where we're coming to the end of that, right? Where it's now getting physically more and more challenging to put more balls on these packages, put more wires in between the compute and the memory element, and thermal limitations for the data movement. It's all kind of conspiring together to sort of limit our ability to kind of scale our way out of this problem. So now we're trying to going back to re-explore some of the older ideas. Can we put some little bit of compute logic in the memory device itself and just offload a little bit of the memory-bound computation and eliminate some of the memory traffic, between the compute and the memory, and see if we can sort of alleviate the problem that way. Okay. And so one of our first efforts in this area is what we call Scalable XL. It's the first in-system demonstrated processing memory. So what Scalable is actually a commercially shipping HBM2 device, that Samsung's HBM2 device, and it's shipping in currently leading-edge AI and high-performance computing systems. And so what we've done is actually we've taken the Scalable DRAM die and sort of pushed apart the DRAM banks and dropped in some programmable compute unit in there that will do some acceleration of FP32, FP16, and INT16 sort of data types, so that you can do some computation in right next to the DRAM banks there. Okay, and so note that we're not trying to replace or displace CPUs or GPUs or TPUs, right? So the transistors and the bleeding edge logic processes are still way faster than the transistors that we have in the DRAM process, perhaps by an order of magnitude. So it doesn't make sense to start moving a lot of the sort of compute-bound task into the processing and memory device. I think that at that point that becomes a decelerator rather than an accelerator, right? So so what we're trying to do is looking at a program that may have a part of it that's heavily memory-bound, and with the memory-bound portion, just grabbing the data, moving into the compute element, and just touching it a few times for compute, and then casting it away, right? So those would be the kind of the optimal type of application that we would like to just keep it on the memory side to do the simple compute, whether it's FP32 or FP16 or INT type processing capability. Okay, And by doing that, what we're hoping to do is by eliminating the data movement and just keeping the compute within the memory device, what we can do is eliminate the data movement, and that could improve the performance and improve the energy efficiency with the in-DRAM processing. Okay. And so we've worked with our industry partners, with an FPGA and GPU systems. But what we show here is that we've integrated this AquaBolt XL device into an Xilinx FPGA. Normally, this FPGA has just the normal AquaBolt HBM device. So we replaced those HBM2 device with this AquaBolt XL HBM device with integrated compute element, right? And so, the limited benchmarks that we show here are some AI and machine learning applications that show the initial investigation that seemed promising, right? That we have performance improvements from 2 to 2.5 times, and latency and energy consumption efficiency improvements on the same order of magnitude. Okay. Due to time constraints, I'm not going to spend a lot of time diving into these details. If you're interested in the details, we have our papers have been published in 2021 ISSCC and ISCA, as well as we have a presentation at Hot Chips for 2021. So you can look up some of the details in those presentations. Okay, so that's basically the processing and memory, right? So now I'll talk a little bit about AXDIMM. Well, what is AXDIMM? Well, it's basically what I refer to as near memory compute. So processing memory, as I explained, right, it's really an idea to try to keep the computation in the memory device itself by adding the computational logic in the memory device itself. But that architecture is not very extensible to all the different type of memory subsystems. For example, server subsystems with DDR4 and DDR5 devices, they have a rank of devices, either 8, 9, 10, or 18 or 20 devices. And to be able to do sort of in-memory compute in that case, you would have to kind of bit splice these a cache line and sort of send in the data to the memory devices in little tiny slivers of stuff, and to have the compute done over there in this manner. So that adds a level of complexity. So to try to make things simpler, what we try to do is really we would place a data buffer that would see the data locally on the module itself and do the acceleration there. So the compute element would be in this data buffer as opposed to be in the memory device itself. The idea is still the same, right? It's trying to alleviate the bandwidth bottleneck between the memory module and the host system by trying to take advantage of the parallelism and the bandwidth on the module itself. Okay. And again, the initial evaluation results are also promising. It shows that we have performance gains as much as 1.8x and appropriate energy efficiency improvements as well. The initial evaluation platform that we use, again, is a sort of Xilinx FPGA. So we got these ginormous memory modules with a FPGA in there acting as the AXDIMM data buffer that captures the data, does the processing, and then moves the data back to the memory devices without interaction with without a lot of tightly coupled interaction with the host CPU. What we did is that we enabled some personalized recommendation application, as well as a deep learning recommendation model using AXDIMM. And as you see here, so with a 2-rank sort of AXDIMM, we attained a performance of 1.8x. So, and we sort of simulated, we didn't actually build the 4-rank and 8-rank AXDIMM, but we sort of simulated the performance implication. What we saw was that this application is very much memory bandwidth bound. So if we provided the additional parallelism and bandwidth on the module itself, this application could well take advantage of it, and we could see performance gains of 3.5x and 6.9x. Okay. some of the references are also provided at the 2019 ISCA paper. And again, if you're interested in this topic, we have our results have been discussed along with the HBM PIM evaluation in our ISCA paper as well. Okay. So looking at the sort of near developments for in-memory and near-memory compute, what we're trying to do is look at the couple things. We're trying to make the existing implementation more power efficient and energy efficient and performance improvement. And also, we're trying to explore extending this architecture to different types of memory. For example, right now it's an HBM device, and it's targeted for AI and machine learning applications. So it's designed to accelerate FP32, FP16 type of application. Now, if we could extend it, for example, into LPDDR devices, for example, that would target a different set of applications, which the FP32 and FP16 type of acceleration may not be as important, whereas smaller integer type accelerations for sort of mobile applications may be more important. So we could look at different types of acceleration for different types of memory devices. And we're trying to extend our hand in collaboration with the industry to offer this architecture. We could, if this architecture is good enough, we can go ahead and standardize it and implement it in different type of memory devices. Or we invite the industry to come in and look at it and propose alternative architectures that may be better than the existing one that we started with. Okay. So that's sort of the quick summary of the processing in memory and near memory. Now, quickly talking about CXL devices. So just very quickly, the CXL, I'm sure you've seen a few of these slides a few times. Type 1 device is just an accelerator. Type 2 device, an accelerator with memory. So the AXDIMM that I spoke about a little bit earlier would dovetail nicely as a Type 2 accelerator device with a CXL interface. But that's for the future. And today, we're going to spend most of our time talking about the Type 3 device with just the CXL memory. Okay. So this is the Samsung CXL memory type that we've announced. We're considering different EDSF form factors, whether it's E3S or E1S or E3L, right? To be compatible with the CXL2 specification. We will initially be using DDR5 memory and start with 128 gigabyte of capacity to, we're not revealing what our upper limit is at this time. And we're evaluating different types of features such as dual port, and I'll mention that a little bit in a moment. Okay, so obviously memory pooling is heavily on everybody's mind, and we're collaborating with everyone to explore, the industry to kind of bring up these devices to explore direct attach CXL memory, as well as looking at use cases perhaps through a switch. And in the case that we don't have a switch, we're looking again at something with, for example, dual port, that you can basically have the device be configured with 2 ports to be connected to 2 different hosts, and you can pool or share the capacity, if you will, with the 2 different hosts without additional switch needed. Okay. So, so something that is just kind of a palate cleanser, if you will. So most people, spend time with software and what have you. So I just want to kind of bring out something that's kind of interesting, at least to really serious DRAM nerds kind of thing. So for us to go into CXL memory design, in looking at the EDSF form factors, whether it's E1S or E3S, it's going to be quite a new set of challenges, looking at component placement or routing or signal integrity or power integrity or thermal or basically everything. So what I'm trying to motivate here is that if you look at the regular RDIMM on the left-hand side, you have the very nice, very narrow command address buses go up the middle and it's distributed sideways. And the wide data bus is routed sort of vertically, if you will, right? So the width of the module is nicely that you can route this big fat bus this way. For something like the EDSF E1S module, it's a tiny little thin thing. And you start out with a smaller form factor, and now you try to place a lot of components on there. And it's a very narrow module to route a lot of wires, right? So the thing is that what I'm trying to motivate is that EDSFF has been sort of initially designed for like SSDs, NAND devices, in an environment where people consider single-digit gigabyte per second as being very high bandwidth, right? So in the DRAM device application where we use DDR5, we're going to look at 30 to 40 gigabyte per second as something that we're going to try to hit nominally. So in that environment, just think about, as what I spoke to earlier, about the bandwidth constraint. We're going to need to cram a lot of very wires that need to run at very high data rates in this much narrower space, if you will. So it's a much more challenging proposition. So it's going to be very difficult to kind of try to place this, route it, and make sure that everything works properly. But I kind of look at these things kind of philosophically, right? I mean, hard disk drives, evolved from 5.5 inch, 3.5 inch to U.2. And the SSD guys lived with U.2 for a long time, and eventually they'll move to something that's more optimized for them, which would be EDSFF. So for CXL, if you run on memory, well, we have no choice. We have to live with what the industry is providing for us, which would be the EDSFF form factors. And perhaps in the future, as we get more memory application, one day, maybe 10, 15 years from now, we'll go look at something more optimal just for memory and accelerators. Hopefully, the Type 1 and Type 2 CXL devices will have gained some market share for that to be of relevance. Okay. And so I think CXL memory development, obviously, it's exciting. It's a clean slate. It's a brand new canvas for us to do work on. There's a lot of new and interesting things, and I think people have alluded to this quite a lot already, so I won't go back into it too much. But it's very exciting that the media controller is now on the device side, and all the RAS features, security features, thermal, and all the characteristics and the different media types can now be sort of separated from the host. You just have a very nice split transaction interface with the host, and you can put different types of media, or you can put accelerators on the device side. So that makes this thing very exciting to work with, and the possibilities are kind of endless. Okay. Let me quickly go on, some limited time. So I just want to mention one last thing, that Samsung has sort of started a set of software effort to sort of deal with some of the memory tiering issues that people have spoke quite a bit about. And this Samsung's effort is called the Scalable Memory Development Kit. It's a SMDK. So really cut down to the chase, what SMDK provides is really just a framework with two sets of APIs. One is what we refer to as a compatible API, and the other one is what we call optimizing API. So as the SMDK itself, when it starts, it basically creates controlling pools to say, okay, you have this set of memory with one set of characteristics, you have another set of memory with a different set of characteristics with a different tier structure. Applications can choose to use the compatible set of APIs, which this whole space is treated as a flat space. So it basically runs in a compatible way without a modification. It's just memory to it. So you're going to suffer some performance losses, but it works, right? And then as you gain, as you go on and you want to start optimizing for the application performance, then you can start going back to the SMDK and start looking at the different API calls, saying, oh, I can make this request and it will call this tier of memory as opposed to a tier of memory that's farther and longer, right? And these two set of APIs are compatible so that you can easily move from one to the other, right? And longer term will provide things like different type of tiering engine and different pool management. And I won't go too much into it since I'm running out of time, but I think this is just sort of a framework to lay the foundation to do the memory tiering and intelligent data flow and advanced RAS features, okay? And as I mentioned a little earlier, right, we'll have a demo with SMDK at OCP. The engineers have flown in from Korea, and you can grill them at the booth about this software, okay? Okay. All right, so I want to thank you, and basically, don't move data if you don't have to, and we're going to need a lot of collaboration from the software guys to make all this happen. Well, thank you.